Welcome to part two. So you might have heard before that you cannot add apple and orange. Actually, this has a more general rules in physics, which is called dimensional homogeneity. And as you cannot add apple and oranges, similarly in a physical equation, you cannot add uh, two terms that does not have the same dimensions. So if you have an equation, each additive term in the equation must have the same dimension as the other term. Similarly, if it is a dimensionless equation, what would this tell you about each term of this equation? This means that each term in this equation is also dimensionless, or should is dimensionless. So let's look at this part. So basically, in this objective of this lesson is to understand the principle of dimensional homogeneity and how you cannot add apples and orange. So dimensional homogeneity, every additive term in an equation must have the same dimension. So this guy must have the dimension as this guy, as this guy, as this guy. The dimension on the left hand side is the same as the dimensions of the guys on the right hand side. That's called dimensional homogeneity. So basically here I'm just showing you this is an equation of energy. So I'm telling you like the total mechanical energy that's equal to energy due to pressure gradient, kinetic energy, and pressure energy. That's all what it is. So that is like energy, total energy. That's energy due to pressure gradient, kinetic energy, and potential energy. Although each of these guys has like a different equation, but they will all reduce to the same dimensions. So I mean, we did this before. Let's do it again. I mean, we did energy before. So remember, if you remember from last class, like energy, what is energy? Do you remember energy? That's like force time distance, yeah? And what is like force? That's like mass time acceleration time like distance. And this will like what will like mass time acceleration, you can also express it, remember, like velocity over time. That's all these things are equivalent, yeah. Let me delete this guy, it look nicer. All these guys are equivalent, or I could also write it as like m, like distance over time square, yeah. Do you agree? M, this time distance here, time distance here. Yeah. So energy, force time distance. So force, that's like mass time acceleration time distance. So here I can express acceleration and velocity over time. I can express velocity as like distance over time square, and then time distance. What would be like the unit of this guy? So the unit of this guy, that will give me, that's like m here. S, that would be like length square, and t, that would be t minus 2. Okay, not clear. Here s, so that would be like m, that would be l square t minus 2. Yeah, okay. So that is like energy. Energy due to a pressure gradient like this one. That's like Q. And that is equal to pressure times volume. That's what it is. Remember, like, what is pressure? Remember, pressure, that's like force over area. And and volume is just like volume, yeah? So you can express it as something like this. So what is force? Remember, like we have force here, like as you can express force as like m s over the like square, for example. That's like because the over area, yeah. So that's like over area time like the volume. Yeah, we can do this. Yeah. So what will this simplify to? Remember, like here, like this area and volume that will give you like a distance. So here, that would be like m over s square over like t square. Yeah. Or let me just write it to look at the previous one so that you'll see the similarity. So that could be like m s over t square s, and that will give us what we've seen before. So you see here, I start like this force time distance, this pressure time volume. That will give you the energy due to pressure gradient, and then it ended up something like this. Kinetic energy. So kinetic energy, that is like half mv square, velocity square. So that would be like half, and then like m, that's like mass, v square. So v square, that I could express it like s over t square. Yeah, do you agree? And s over t square, that will give me the same things that we've seen. So that's like half m s square over t square. That's what we got here. So that will give us. So what is the dimension of this guy? I mean, nothing like 1. Yeah. So that's like m over L square t square minus 2. So you see like we are different equations, but that's why we can add like this energy due to pressure gradient with kinetic energy, potential energy. So potential energy, that's like mgz like distance. So we know this like m, that's like mass, g like this v over t, and z whatever, that's like the distance. We can express this like as m, we can express it as distance, so z over like t square. Yeah, I'm just expressing the distance here instead of s as z. Yeah, it makes no difference. Yeah, and that would be z. So again, I will get here that, so that's L, that's t, that's m, so m L t minus 2. Okay, so you see like this guy here, oops, is equal to this guy here equal to this guy here equal to this guy here. That is called dimensional homogeneity, and that's why I can say that the energy is equal to like the sum of like these two energy. Yeah? Total energy, and that's why like even though they have different equation, but they have this, all of them has the same dimension because all of these are different like energy units. Yeah. Okay. Let's do an exercise. So use dimensional analysis to verify the dimensional homogeneity of hydraulic head equations. So remember like the hydraulic head, which we did before in the previous lesson, and hydraulic head like H, and I told you like H has that it's so hydraulic head, that's energy, it's an energy, but the energy per unit weight. So basically you divide the energy, so you divide like this guy by weight, by mg. So like you have like, so energy, let's say like energy is equal to mgz. If you divided this by mg, that will give you h. It'll be like that, for example. Yeah. And same with all the other one. So I'm telling you, use dimensional analysis to verify the dimensional homogeneity of the hydraulic head equation. So we know that head, like this constant head, has a dimension of L. So can we verify that all these guys has like the same dimension and can be added together? Yes. Z, that's a distance. So we know that like for this guy, the first term, that has the unit of Z. Okay. So, oops. So that is like the first term here. The second term, pressure over rho g. So can we do this? Yes. So we know the pressure, that is like force over area over like rho g. Yeah. So force, we know that the force is mg, mass time acceleration, yeah, over area like rho g. So like the g will go here with the g. Now the rho, we know that's like mass over area. Rho, that's like mass over volume. Yeah. So the mass will go with the mass. And then we get like volume over area. And that will give us like length. Yeah. Something like this S, which is length. Yeah. So that will give us something in length. Yeah. Distance. Yeah. Volume over area, that's like a distance. Okay. So that is like for this guy here. So he showed that. So this guy here is L. This guy here has L. Can we do this guy? Yeah. So this guy like V square over 2G. So V square, we know that this is S square over T square because velocity square over G, that's like acceleration due to gravity. So we know that acceleration, that is like S over T square. Yeah, so T square will go with the T square, S will go with the S. So we got like an S, and that has a unit of L. Okay, so you see like even these guys, they are different physical, they like they have different physical equation, but they are the same physical quantity, which is what we are measuring here. We are measuring energy, energy per unit weight. That's what we are measuring. Is this a primary or non-primary quantity that we are measuring? It is non-primary. Why? Because it is derived from primary quantity. Actually, it is actually a primary quantity because it's length. Yeah. So we are measuring actually. It's primary actually. It's primary quantity because it's like it has a dimension of length. And here it's funny because like you're telling me, are we measuring energy as length? Yes, we are measuring energy in unit of length. Like energy, the unit of energy is joule, but here this is like energy per unit weight, which will have the unit of length. So I'm measuring energy in length. And in the previous, remember in the previous example where I showed you like something like this and like a sand column here and something like this. Yeah, let's see here. So let's say here. That is like H here. And that is like, let's say H2. Yeah. So you see here H1, that's like energy is higher than H2. So I'm measuring energy here in terms of length. That's what it means. Okay. So here, this is another practice problem. I'm telling you, use dimensional analysis to verify the dimensional homogeneity of Bernoulli equation. So again, you can solve this, and after you solve this, you can go to the lecture note and check the solution. So here, like if you go to the lecture note, you can, oops, you can like check the solution. I have the solution there, but don't look at the solution, just try to solve it. And then once you do this, then you are ready for your homework problem. Use dimensional analysis to verify the dimensional homogeneity of this equation, and then like I'm asking you some answers just to see if you understand like the concept that we covered in this lesson and in the previous lesson. Again, if you can solve this exercise, if you can solve this practice problem, you should be able to solve the homework problem, and then you will find in the exam something similar that you should be able to solve. So that is it for lesson one, which was a review of which was a review of dimensional analysis. We basically did dimensions and unit. We understood what's the difference between these two. So uh, so dimension basically is like a measure of a physical quantity. It could be a primary quantity or it could be like a non-primary quantity. And the unit is, and this is dimension, you're just measuring it without putting like a number to it. Like units, that's when you start putting a number to it. Yeah. And we looked at dimensional homogeneity, the principle of dimensional homogeneity. In next lesson, we will learn about like pi theorem, and I will like it be, we will take this to the next level. Like we basically take dimensional analysis to the next level beyond what you did in as an undergraduate student in like fluid mechanics, for example. Okay, and we will see the application of this in physical models. So see you next